At 11:24 in the morning, local time, on the 30th of July, the sixth largest earthquake ever measured by modern instruments tore open the seafloor off the coast of Russia's Kamchatka Peninsula. Magnitude 8.8, a rupture so long and so violent that it shook for the better part of 4.5 minutes, not seconds, minutes, while the ground beneath one of the most remote, most seismically watched patches of coastline on Earth simply refused to stop moving. Within minutes, tsunami warnings were racing across the Pacific faster than the wave itself, reaching Japan, reaching Hawaii, reaching the west coast of the United States, reaching countries as far away as Chile and French Polynesia. Millions of people were told to evacuate. And when scientists went back afterward to actually reconstruct what had happened deep beneath the waves, they found something that didn't just make headlines. It made them go back and question assumptions that had stood largely unchallenged for 70 years. This is the story of an earthquake that, according to the scientists who study these things for a living, broke patterns we thought we understood. Not broke as in destroyed a city, though it came uncomfortably close to doing exactly that. Broke as in shattered a model. Rewrote a textbook paragraph. Forced researchers publishing in some of the most prestigious scientific journals in the world to use words like unusual and complex, and to openly admit that the recurrence of great earthquakes may not follow the regular, predictable patterns we've relied on for decades of hazard planning. If you live anywhere near a coastline touched by the Pacific Ocean, this is a story you should actually understand, because it isn't really about Russia. It's about what the ground beneath every subduction zone on the planet might be capable of whenever it decides the time has come. Let's start with where this earthquake happened, because location is the first clue to why it mattered so much. The epicenter sat just off southern Kamchatka along the Kuril-Kamchatka Trench, a stretch of ocean floor where the Pacific Plate is diving underneath the North American Plate at roughly 80 millimeters a year, one of the fastest, most seismically restless convergent boundaries anywhere on Earth. This is not an obscure or forgotten fault. It's one of the crown jewels of the Pacific Ring of Fire, a region that has produced over 30 earthquakes above magnitude 6.5 in the past century alone. And it has a very specific, very well-documented history that made this year's rupture feel less like a surprise attack and more like the return of an old and familiar threat. Because in 1952, almost exactly the same stretch of seafloor ruptured in a magnitude 9. Some estimates place it as high as magnitude 9.0, earthquake that sent a devastating tsunami racing across the entire Pacific Basin. That 1952 event is the benchmark. It's the earthquake every seismologist studying Kamchatka has spent decades comparing everything else to. And when this year's magnitude, 8.8, earthquake ruptured, researchers quickly discovered that its aftershock zone overlapped almost precisely with the aftershock zone from 1952. Not roughly, not approximately. The rupture extended about 500 kilometers from the epicenter, propagating southwestward, and that 500-kilometer stretch of broken fault lined up remarkably closely with the roughly 500-kilometer rupture length recorded in 1952. Both earthquakes even nucleated, meaning they started breaking, at the same northeastern end of the fault, before tearing southwestward from there. Researchers who later reconstructed the rupture using teleseismic back projection and underwater acoustic recordings called this an unusual similarity, and concluded that ruptures in this region may be controlled by some deep structural feature of the megathrust margin itself, some permanent physical characteristic of the fault that channels its ruptures down the same path again and again, event after event, decade after decade. If that were the whole story, it would already be remarkable. Two great earthquakes, 73 years apart, breaking almost exactly the same patch of ocean floor in almost exactly the same direction. But here's where it gets genuinely strange, and where the broke-the-rules framing starts to earn its keep. 73 years is not a long time, geologically speaking, for a fault segment to reload enough stress to produce another earthquake of nearly the same scale. Subduction zone recurrence intervals, the time it typically takes for a fault to build up enough strain from plate motion to rupture again in a comparably sized event, are usually measured in centuries, not decades. Using a convergence rate of about 80 millimeters a year for this specific stretch of the Kuril-Kamchatka Trench, researchers calculated that over those 73 years between 1952 and 2025, the fault could have accumulated a maximum slip deficit, essentially a backlog of unreleased motion of somewhere close to 6 meters. That's a substantial amount of stored energy to release in a relatively short window, and it strongly suggests that in subduction zones with unusually high convergence rates like this one, the recurrence interval for great earthquakes may be far shorter than the textbook assumption of a few hundred years, potentially under a century. That's the kind of finding that makes hazard planning agencies around the Pacific quietly go back and re-examine every timeline they've published. And then there's the slip itself, how far the rock actually moved during the rupture. When scientists modeled the finite fault slip distribution of this year's earthquake, using both teleseismic data and satellite observations combined with deepwater tsunami recordings, they found something that seemed almost contradictory. The peak slip in the 2025 rupture, meaning the single, largest amount of displacement recorded anywhere along the fault, was actually greater than the peak slip estimated for the 1952 event. In places, the localized maximum slip reached somewhere in the range of 30 to 40 meters, with multiple patches of the fault exceeding 10 meters of movement. That is an enormous amount of displacement, some of the largest slip values ever recorded for an earthquake of this class. And yet, and this is the piece that made scientists sit up, despite that greater peak slip, the tsunami this earthquake generated was noticeably weaker than the one produced by the 1952 event. Weaker than models based purely on earthquake magnitude and slip would have predicted. A bigger localized rupture, in some ways, and a smaller wave. That is not supposed to happen, at least not according to the simple intuitive version of tsunami physics most people carry around. The idea that bigger earthquake generally equals bigger wave. What it actually revealed is something scientists have long suspected, but rarely gotten to observe this clearly in a single, well-instrumented event. That the amount of energy released by an earthquake and the amount of vertical seafloor displacement that actually reaches the ocean floor in a tsunami-generating way are not the same thing. You can have enormous slip deep within the fault in a way that shows up powerfully in seismic recordings and in models of the earthquake's overall energy release, without that slip translating efficiently into the kind of shallow, near-trench seafloor uplift that actually shoves the water column and builds a devastating wave. One research team studying the event specifically pointed to something called limited shallow rupture, meaning that even though the deeper portions of the fault slip tremendously, the shallowest part, closest to the trench, and closest to the ocean floor where displacement most efficiently converts into tsunami energy, didn't rupture nearly as extensively. That single structural detail may be the entire reason the Pacific didn't experience a repeat of 1952's devastating ocean-crossing tsunami this time around, even with a nearly identical rupture length and, in places, even greater slip. It's a distinction with enormous consequences, and it's exactly the kind of nuance that a magnitude number alone can never tell you. Two earthquakes can share almost the same rupture zone, almost the same length, comparable or even greater displacement, and produce wildly different consequences for the people living along the coastlines those waves eventually reach. There's another feature of this earthquake that scientists flagged as genuinely unusual, and it has to do with how the rupture unfolded through time. This was what one major scientific paper, published in the journal Science, specifically described in its title as a simple unilateral rupture, meaning the fault broke predominantly in one direction, propagating southwestward from its starting point near the northeastern edge, rather than breaking in a complex multi-directional stop-and-start pattern the way many great earthquakes do. Simplicity, in this case, doesn't mean small or unremarkable. It means the rupture had an unusually clean, coherent structure for an earthquake of this magnitude, unfolding over roughly 270 seconds, about 4.5 minutes, as it tore southwestward across a fault plane estimated at somewhere between 390 and 600 kilometers long and 140 to 200 kilometers wide. 4.5 minutes of continuous rupture. Try to sit with that for a moment. Most earthquakes that cause noticeable shaking last a matter of seconds. A genuinely large, damaging quake might shake for 20, 30, 60 seconds. This fault kept tearing, kept releasing energy, kept moving for close to 5 full minutes, propagating across a stretch of ocean floor longer than the distance from Los Angeles to San Francisco. And the fact that it did so in this clean, coherent, unilateral fashion, rather than breaking apart into disconnected sub-events the way many complex megathrust ruptures do, is itself part of what researchers found scientifically significant. A rare, almost textbook clean natural experiment in how a single great earthquake propagates across a very long fault segment, providing exactly the kind of high-quality data that seismologists spend entire careers hoping to capture. Aftershocks played their own strange role in this story too, and this is a detail that deserves real attention, because it touches directly on one of the oldest, most tantalizing dreams in seismology: earthquake prediction. Beginning roughly 10 days before the main shock, the region experienced a swarm of foreshock activity, including a magnitude 7.4 earthquake on the 20th of July, itself a genuinely large earthquake in its own right, one that in almost any other context would have been the lead story on its own. In total, the sequence leading up to the main event included over 400 smaller earthquakes measuring magnitude 4 or greater. And crucially, this pattern: intense foreshock activity concentrated at the same northeastern end of the fault, where the eventual main rupture would nucleate, mirrored almost precisely what happened before the 1952 earthquake as well. The same location, the same style of foreshock buildup, the same eventual nucleation point. Twice, 73 years apart, the fault seems to have telegraphed, at least in hindsight, roughly where it intended to finally let go. This is exactly the kind of pattern that earthquake scientists dream about finding, and also exactly the kind of pattern that history has taught them to be deeply cautious about overinterpreting. Foreshock sequences that precede major earthquakes are only identifiable as foreshocks after the fact. In the moment, a magnitude 7.4 earthquake is indistinguishable from any other significant, potentially standalone earthquake. Nobody can currently look at a swarm of smaller quakes and reliably say, with actionable certainty, in 10 days, an 8.8 will strike here. But when a real-world case study emerges, showing the same structural fault segment producing a eerily similar foreshock behavior twice in a row, decades apart, it adds serious weight to research into short-term earthquake forecasting, and it gives scientists a genuine, concrete case to study, rather than a theoretical one. Now, let's talk about what actually happened once the fault let go, because the human story here is almost as strange as the geophysics. The earthquake struck at a depth of about 21 kilometers, shallow enough and powerful enough that it registered as the most powerful seismic event on the planet since the catastrophic 2011 Tohoku earthquake in Japan, and one of the 10 strongest earthquakes recorded since 1900. In Kamchatka itself, the shaking reached a maximum intensity of 9 on the modified Mercalli scale, described as violent, strong enough that at least 250,000 people in the region felt severe, damaging shaking, according to United States Geological Survey estimates. Petropavlovsk-Kamchatsky, the nearest large city, home to more than 180,000 people, took real damage. A kindergarten building was damaged. At least 4 people were injured, and 55 homes and several other buildings were damaged in the immediate area. In Sakhalin Oblast, further south, at least 106 buildings were damaged, and several port structures were destroyed outright by the tsunami that followed almost immediately along the nearby coastline. The town of Severokurilsk flooded, not for the first time in this earthquake's aftermath sequence, but repeatedly, as successive waves and aftershocks continued to hammer the same stretch of shoreline in the days that followed. And then, almost as if the planet wanted to underline just how much stress this region was under, the Klyuchevskoy volcano erupted just hours after the main earthquake. Scientists were quick to clarify that the eruption wasn't directly caused by the earthquake. Klyuchevskoy is one of the most active volcanoes on Earth and erupts regularly regardless of seismic triggers. But the timing was, in the words of observers watching it unfold, almost too cinematic to be believed. Lava descending the western slope, glowing against the night sky, while tsunami sirens were still sounding along the coast below. A few days later, on the 3rd of August, a magnitude 6.8 aftershock struck the nearby Kuril Islands, and just hours before that aftershock, the Krasheninnikov volcano erupted for the first time in 600 years. 600 years. The head of Kamchatka's volcanic eruption response team noted that this eruption, too, may be linked to the stress redistribution triggered by the earlier magnitude 8.8 earthquake, even if it wasn't a direct, instantaneous cause. This is a region where the crust itself seemed to be working through an enormous release of accumulated pressure, expressing it through fault ruptures and through volcanic vents almost simultaneously. Then came the tsunami, and this is where the story takes its most counterintuitive turn. Given the earthquake's sheer size, tied for the 6th strongest ever recorded by modern instruments, and given how closely its rupture zone matched the catastrophic 1952 event, every tsunami warning center around the Pacific treated this as a worst-case scenario in the making. The Pacific Tsunami Warning Center issued its first tsunami threat message within just 10 minutes of the earthquake. A full tsunami warning calling for evacuation went out for Hawaii. Warnings were issued for the western Aleutian Islands and for Northern California. Advisories went out for Guam, American Samoa, the Eastern Aleutians, and the Alaska Peninsula. In Japan, evacuation advisories reached an extraordinary 2 million people along the Pacific coast. Rail lines were suspended, and flights were grounded at Sapporo's airport. A level of precaution rooted directly in the lessons of the 2011 Tohoku disaster, when Japan's post-Fukushima policy essentially became, when in doubt, do not risk it. And then, as the actual wave data started coming in from tide gauges and deep ocean buoys scattered across the Pacific, something became clear that surprised almost everyone outside the small community of scientists who understood the shallow rupture nuance we talked about earlier. The tsunami, while real, and while it did travel the entire width of the Pacific Ocean, was far weaker than the earthquake's magnitude alone would have suggested. In Hawaii, which braced for the most severe impact of anywhere in the United States, the largest waves reached about 5.7 feet in Kahului on Maui and 4.9 feet in Hilo. Significant, capable of real damage in low-lying areas, enough to justify every evacuation order that went out. but nowhere near the kind of city-erasing wave that 1952, or that scientists' worst-case modeling based on the earthquake's raw size, had prepared people to fear. In Crescent City, California, a town with a long and painful history of tsunami damage, waves reached about 3.6 feet, still enough to cause over $1 million in harbor damage and disrupt local fishing and shipping. Operations, a reminder that you don't need a towering wall of water to cause serious economic harm. Japan recorded tide gauge readings as low as 32 centimeters in some locations. The tsunami's reach was genuinely global. Swells were detected as far away as French Polynesia, and warnings extended to Mexico, Chile, Indonesia, and China. But its height, almost everywhere outside the immediate source region, fell well short of the catastrophic scenario that a magnitude 8.8 earthquake, rupturing the same zone as a magnitude 9 event 70 years earlier, would ordinarily suggest. There was one striking exception, and it's worth mentioning because it illustrates just how localized and unpredictable tsunami run-up can be even within a single event. In a steep, narrow river valley near Vestnik Bay, close to the earthquake's source, the tsunami surged to a documented height of 33.1 meters over 109 feet. That's not a typo, and it's not the tsunami's overall height across the Pacific. It's a dramatic illustration of how coastal and underwater topography can funnel and amplify a wave into something monstrous in one specific location, even while the same. Tsunami arrives as a modest, manageable swell just a short distance away. It's the same lesson coastal engineers have learned again and again. There is no single number that describes how big a tsunami is. There's only how big it gets in each specific inlet, each specific harbor, shaped by the seafloor and coastline it happens to encounter. In the end, remarkably, given the scale of the earthquake, the human toll was extraordinarily light. Official tallies describe this as the largest earthquake ever recorded to cause no direct casualties from either the shaking itself or the resulting tsunami. The deaths and injuries that did occur were indirect. One woman in southern Japan died in a car accident during an evacuation, and around 20 others suffered mostly heat-related injuries while sheltering or evacuating during the response. Given that this was one of the 10 most powerful earthquakes humanity has ever measured with modern instruments, an earthquake that ruptured 500 kilometers of ocean floor and shook continuously for 4.5 minutes, the fact that it produced so few direct casualties stands as a genuine triumph of the very warning systems and evacuation infrastructure we've spent the last 70 years, since 1952, building specifically because of what this same stretch of fault did the last time it let go at this scale. So, what does it actually mean to say this earthquake broke the rules of science? It doesn't mean scientists were left with nothing to explain. It means the explanations they've reached for decades. Simple relationships between earthquake magnitude and tsunami size. Tidy assumptions about how long it takes a fault segment to reload enough stress to rupture again. Clean expectations about how ruptures propagate and where their energy actually goes. All of those got measurably more complicated this year. The recurrence interval math suggests great earthquakes here might repeat far sooner than the textbook. Centuries-long timeline implies. The slip data shows that a rupture can move more rock than its predecessor and still generate a weaker tsunami, because where the fault slips matters as much as how much it slips. The foreshock pattern offers a tantalizing, still unproven glimpse of predictability nested inside a phenomenon we generally treat as fundamentally unpredictable. And the near-perfect geographic overlap with the 1952 rupture suggests that somewhere deep in the structure of this particular stretch of the Kuril-Kamchatka Trench, there is a physical feature, a bump, a boundary, a change in the rock itself, that is quietly, patiently dictating where and how this fault will keep breaking, earthquake after earthquake, for as long as anyone has been watching, and almost certainly for a very long time after we've stopped. There's a broader thread here too, one that connects this single earthquake to a much older and more uncomfortable conversation in seismology. The question of whether great earthquakes on a given fault segment really do behave like a metronome, releasing roughly the same amount of stress at roughly the same interval, or whether that whole framework, the one hazard maps and building codes around the Pacific, are quietly built on, is a convenient simplification of something far messier. The classic model, going back decades, imagined subduction zones breaking into fairly well-defined segments, each one accumulating strain at a steady rate and releasing it in a fairly predictable, great earthquake every so many decades or centuries, almost like a geological heartbeat. It's a model that made hazard planning tractable. You could look at the last big earthquake on a given segment, estimate the loading rate, and produce a rough window for the next one. Kamchatka's 2025 rupture doesn't destroy that model outright, but it does something almost more unsettling. It shows the model can be simultaneously right and wrong at the same time. right? In that the rupture reused almost the exact same fault segment, nucleating in almost the exact same place as the earthquake 73 years before it. Wrong in that 73 years is a startlingly short interval for a segment of this size to fully reload. And in that, the relationship between how much the fault slipped and how large a tsunami it produced didn't scale the way the simple version of the model would predict. The rupture zones of historic great earthquakes in this region, researchers have noted, generally abut one another rather than overlap, which had long suggested a fairly orderly, quasi-regular sequence of ruptures, marching along the trench over time. The fact that 2025 broke that pattern by reusing 1952's exact footprint is precisely the kind of anomaly that keeps seismologists up at night, in the best and worst sense of that phrase. It also matters enormously for how monitoring networks are built going forward. An earthquake this well recorded, captured by teleseismic stations around the globe, by GPS and satellite geodesy measuring millimeter-scale ground deformation, by hydroacoustic sensors listening for the sound of the rupture traveling through the ocean itself, and by a dense global network of tide gauges and deep ocean pressure sensors tracking the tsunami's actual height in real time as it crossed the Pacific, becomes a kind of gift to the scientific community, even as it terrifies the people who lived through it. Every one of those data streams gets fed back into the models that determine how quickly the next warning goes out, how large an evacuation zone gets drawn, and how much residents of Kamchatka or Hawaii or Crescent City or anywhere else along this ocean's rim can trust the alert on their phone the next time the ground starts to move. The scientists who spent the months after this earthquake poring over its rupture history weren't just satisfying academic curiosity. They were quite literally rewriting the assumptions that the next tsunami warning, wherever and whenever it comes, will be built on. That's the real headline. If you strip away the drama of the wave heights and the evacuation orders and the volcano erupting on cue in the background, like something out of a disaster film. A fault we thought we understood, in a place we've studied intensely for over 70 years, did something in 2025 that forced working scientists, the people who write the papers the rest of us eventually read as settled fact, to go back to their models and admit that the recurrence of great earthquakes may not follow the regular patterns hazard planning has long assumed. If that's true here, on one of the best instrumented, most historically documented subduction zones on the planet, it raises an obvious and uncomfortable question about every other great fault ringing the Pacific that we understand far less well. Cascadia, Nankai, the faults off Chile, off Alaska, off Indonesia. If Kamchatka can still surprise us after 70 years in a nearly identical repeat performance, the honest answer is that we are still, in a very real sense, just beginning to understand the rules these faults actually play by. And the ground beneath every coastline on the Ring of Fire is quietly, continuously working out its own next move on a schedule that may be shorter, stranger, and far less regular than we've been telling ourselves.